Next, we have Professor Giannakis. He's a fellow of IEEE, professor at the University of Minnesota, where he's the McKnight Presidential Chair in ECE and has served as the director of the Digital Technology Center. His general interests span the areas of statistical learning, signal processing, communications, and networking. He's a recipient of numerous awards, including the Signal Processing Society Norbert Wiener Society Award, Eurasip's Papulis Society Award, the Technical Achievement Award from SPS and from Eurasip, and the IEEE Fourier Technical Field Award. He's a member of the Academia Europea, and a fellow of the National Academy of Inventors, the European Academy of Sciences, and Eurasip. Professor Giannakis.
Good afternoon. Thanks for the invitation once again. The title of my talk comes in two pieces. The top one is part of what I was I asked and granted to present, a basic paper and major contribution that Bhaskar Rao and his group had on transmit beamforming using finite rate feedback. That's the title. It was a smart incorporation of vector quantization, the last three dots. But the subtitle is Where Minds Meet and Inspire One Another and Complement One Another. I want to thank the three students back then in mid-2000, Shengli Zhou, Pengfei Xia, and Zhengdao Wang, and corresponding funding from the National Science Foundation and Army Research Laboratory. These three students were involved in research related to the major contribution by Professor Rao's group. And one of them is here, and I want to thank him in particular for his help with the initial set of slides, Pengfei Xia. So difficult questions. He will come forward, I hope. So let me start by trying to give some context for the title of this presentation by discussing the vision around the turn of the century. So for commercial communication systems, the dream was to communicate anywhere, anyone, anytime with any media. And similar or more things were desired from tactical communication systems to be more reliable, covert, and exhibit robustness to adversaries, or low probability of intercept and jamming. So a landmark, I should say, advance back then was the notion of multi-antenna communication systems that gave rise to what is abbreviated as wireless MIMO, multi-input, multi-output systems. And at the very beginning, it was recognized that it allows for diversity in different forms, in time, in frequency, or in space. If you look at the amplitude of the communication link, h tau, versus time or frequency, then you will see that if you have only the red channel, many times you may undergo fades, okay, if you go around buildings or other structures. But it's unlikely two fades to happen in both the red and the green, because if you have two channels, not everything will be in fade, hopefully, or more. So diversity is the ability to create multiple copies. Time and frequency diversity come at the expense of bandwidth expansion. But antenna diversity may cost a bit, but incurs no bandwidth expansion. That's why people like. So diversity was known to increase with the product of the number of transmit antennas T and receive antennas R. And likewise, the data rates and the bandwidth increases with the minimum of NT times NR. This is when I was preparing the slides, the sad news came that the inventor of this result on the ergodic capacity, Gerard Foschini, must be resting in peace at this point, but he was the one who has to be credited with this result. And if the channel is known at the transmitter, the channel from transmitter to receiver is estimated at the receiver, but is known also at the transmitter perfectly, then these great results on capacity can be attained. So these open loop systems, after recognizing the difficulty of having information on the channel, led to people looking into closed loop systems. But before, let me ask myself whether perfect channel state information, or CSI, that we would love to feed back to the transmitter, is this realistic in practice? And the answer is not really, simply because there are estimation errors, there's feedback delay, you're trying to catch up. The channel varies faster than your feedback loop, so that is not really. Then why do we like CSI? Well, how about we don't ask for CSI at the transmitter? And that's what happens with space-time coding. That leads to pessimistic designs. So that one is not good either. So people started thinking about partial CSI. So they said, okay, it may be a good idea if the transmitter at least knows the channel mean or the channel covariance. And a number of people contributed to this extent. That's one form of partial channel state information. But that was the second approach, was to take advantage of the feedback loop and feed back from the receiver to the transmitter a finite number of capital B bits per fading block. If you feed the entire, the perfect channel from the receiver to the transmitter, that corresponds to feeding back the analog values. That means you require infinite bits. So that is impossible because you must be constrained by the bandwidth of the feedback link. So finite rate is basically the way to go in this case. So the context that that paper started from was that of transmit beamforming. So you have on the left an information symbol, S, and it goes through NT transmit antennas. Before getting out, is multiplied by a W1 star, W2 star, WNT star weights. And this is called beamforming vector. To not increase the power, you normalize the norm to be 1. So it's the power of S remains unchanged. And then you go through the channel over the wireless link, and then the superposition is received at the transmitter side. Now, the beamformer to select is often viewed as a bunch of beamformers, capital N, depends on how many bits you are allowed over the feedback loop. Because if you allowed B bits, then you can have a binary description of each beamformer of this W by 2 to the B possible beamformers. So capital N equals 2 to the B are the possible candidate beamformers. And the collection of them is the code book, or the beam book, if you like, that can become known at the transmitter side. So of course, if you have infinite CSI, the best beamformer vector WI is the channel itself. So you're matching what you're transmitting. So it's a match filter at the transmitter side. but that's not desirable or realistic, as we said. So what is really important is to analyze the performance with finite rate channel state information at the receiver side. Okay? So for Gaussian IID fading, first of all, we have to realize that even for non-Gaussian, that the performance in terms of average signal-to-noise ratio depends on the codebook design, depends on what W you're going to select for a given channel. And the approach that people took early on were using minimax designs, so basically, or average receive SNR. So you look intuitively for the worst case between pairs of beamformers, Wi, Wj. So if this one is high, or if this one is low, they are orthogonal, so they're not too close, too identical. So that's more desirable. So you want to look at the maximum inner product of the Wi, Wj, and then minimize overall possible Ws. So these are basically points, Wi, Wj, because they are unit norm vectors. They are points on a hypersphere. And this maximization of this inner product, Wi, Wj, is tantamount to minimization to the chordal distance, as it's known. And the other term for solving this problem is Grassmannian line packing. Now, what are the problems here? The problems are that the channel does not show up, you can tell, in the design of the beamformer, which is counterintuitive. As a matter of fact, because the phase is uniformly distributed, then you justifiably don't need the channel per se, but that's intuitively not meaningful. In addition, it's impossible to capture correlated channels in this codebook design. Okay? And the worst is that this minimization problem is really difficult. So you have to randomly draw some beamformers and then check this min-max value and then redraw and select the one that has the best, the optimum min-max value. In special cases, there have been special cases of number of transmit antennas and number of receive antennas have been closed-form solutions and analytical findings. But now, let me tell you, this is the background. So this is the context. The context is wireless was coming up, early 2000, multi-antenna systems gained popularity, knowledge of the channel at the transmitter side was appreciated as something very useful to improve capacity and diversity, and difficulty to design beamformers when you are prescribed with a certain number of bits, B. So how do you optimize them? What's an optimum set of beamformers? That's the real question. So around 2000, actually, if you look at the November 2004, this is the first Asilomar conference where the ideas behind this paper on vector quantization for transmit beamforming by Rao and Bhaskar Rao. And I repeat the subtitle of my talk for the following reason. Around that time, the same things were happening in my group from the authors that I mentioned, or very related, surprisingly. As a matter of fact, if one goes to look also at the journal papers, the first submissions were sometime in 2004. Something was very nice happening in 2004. And, for example, Greece hosted the Olympics. The Greek soccer team, won the European Soccer Cup. And, in the wireless, all these beautiful ideas were coming forward. So I'll start first to tell you what Shengli Zhou and Pengfei Xia did, and then I'll go back to what happened in San Diego. So we started from an instantaneous symbol error rate for MRE PSK, but any constellation works out. And if you look at the average signal-to-noise average symbol error rate, you need the probability density function of the chordal distance that I was talking earlier. And this is possible to provide, to come up with a lower bound on this chordal distance by adopting some geometrical arguments by Mukavili and come up with a lower bound of the average symbol error rate that applies to all code words. And if you have good code words, you can approach this lower bound. And if you remember, the chordal distance is the inner product of this W with H. Okay? Now, this is what basically we found, that an average lower bound for the symbol error rate can be obtained if you tell me the number of transmit antennas in closed form and the number of bits that you're going to dedicate for the feedback channel. Give me a number of bits, number of transmit antennas, I'll tell you a lower bound of the symbol error rate. Yes. So this is accurate for for B small and asymptotically tight for a perfect CSI. So this is the symbol error rate versus SNR, perfect CSI, 2, 3, 4 number of bits. You see the actual is the blue symbol error rate, and the lower bound is the red, so they are very close. So these are useful. And then we basically asked another question. If we have an SNR drop whenever you have quantized feedback relative to the perfect CSI. We have a drop in the CSI. How much we have to boost the CSI to come up even with the perfect CSI result. And there are different methods, but a useful approximation is at the bottom. Again, if one looks at the number of bits to feedback and the number of transmit antennas, we can give you the loss over signal-to-noise ratio. And what is the message is that the power loss decays exponentially with the number of feedback bits. And that is verified here with 4 transmit antennas and 4 bits transmitted, 4 different beam words. And then the lower bound is less than 324. So we know exactly how much we have to boost our power to come up with a desirable symbol error rate. Now, here comes the inspired solution by Bhaskar Rao's group. So here is the quantizer output, the maximum of this inner product that we talked about. So you're estimating the channel of the transmitter. You're selecting the beam former that basically maximizes this inner product. And this inspired Bhaskar Rao to come up with what is known as the mean square weighted inner product in their paper. And that basically maximizing this ensemble value over all possible code books yields the optimum code book in this case. So this alpha hat is a scalar that depends on the transmit power and depends therefore on the SNR. Now, the code book is basically relying on a generalized Lloyd's algorithm. Okay? So for those of you that are familiar with K-means and clustering, the K-means relies on the average mean square error distortion. This is basically permeating benefits of vector quantization from source coding that was known to the design of beamformers. And there are many beautiful things. The trick, the algorithm at a high level description is basically to alternate between updating the regions, the cell regions or the clusters, or the Voronoi cells, as they are called in source coding, to assign channel realizations to nearest code words using this approach, and then update per region code word the centroid. How? By picking up, turns out, the maximum eigenvector of the channel correlation matrix. So if you know the channel correlation matrix at the receiver side, basically you do an eigen decomposition to find the highest, the eigenvector corresponding to the maximum eigenvalue, and that's your centroid. What do you buy by this? The difficult optimization problem I was alluding earlier, and the fact that you cannot find code books for correlated channels can be done with this inspired vector quantization approach. So you can have local convergence to monotonically decrease, guaranteed, meaning that at every iteration you get to a better solution, or not worse solution, I should say. And this is thanks to this inspiring work. Now, the second part is that it applies to all signal-to-noise ratio, because this constant depends on the SNR. That could be a challenge, though, because every time the SNR changes, you have to redesign the codebook, which was challenging. And that prompted a second mean square inner product metric, which is very similar to the one we have derived. And this is not SNR dependent. And it is best at medium and high SNR. You see here the ergodic capacity normalized relative to the perfect CSI. So the perfect is 1, the higher the better, versus average transmit power. And then you see, as you increase the number of bits, you quickly approach the perfect CSI case. And also, this without the constant, the MSIP at low or high SNR approximates the MWSIP. And guess what? It also approaches the mean square error that we talked earlier. Actually, it broadens the scope. It's a special case. They coincide if the channel is real, but it broadens the scope of the mean square distortion. So I talked already about the average symbol error rate loss. Here, the contribution from Bhaskar's group comes from a very strikingly similar result. So if you approximate the loss incurred in ergodic capacity for high resolution, that means large enough B, and for high SNR, then you have an exponential decay as you increase the number of bits. So pretty much like the symbol error rate, average symbol error rate that you saw earlier, even the approximate loss in ergodic capacity is governed for this quantized system in this simple, very intuitive form. Okay. There are numerical results. I will not. Then there are extensions from Professor Rao's group and our group on MIMO spatial multiplexing. This is one of the authors you saw earlier. The outage probability, in addition to the capacity, Professor Rao's group came up with similar results on the outage probability, and the bit error rate is basically like our symbol error rate. And people have also connected codebook designs in practice with the Welch bounds, and I don't have time to talk about it. But also there are possibilities where if you have n for special selection of number of bits, n equals 2 to the b, and special selection of the number of antennas, you can have analytical solutions achieving the Welch bound. So I have to say that both of us, I don't know about Professor Rao's, but should have filed a lot of patents. We would have been very successful in this category because the popularity of this work to multi-antenna communications has been really major. It has been widely adopted by industry. The long-term evolution standard and the 5G new radio contain explicitly precoding matrices. They're called PMIs, or precoding matrix indicators, to support up to 32 ports and 10 to 20 or up to 100 feedback bits. And as millimeter waves become more popular, since we need high directionality, beamforming is even more useful for 5G. And designing such beamformers is really important. Needless to say that billions of devices in use are utilizing this. So that's why the comment about patents. Now, if I want to wrap up what is the contribution of this vector quantization approach to transmit beamforming, I will say that people knew the role of vector quantization for source coding and for path recognition that was taught back then in electrical engineering. And people were adopting similar algorithms for k-means or clustering. Okay? Now, what this work brought to bear is how vector quantization can help design of feedback systems in wireless multi-antenna communications and make it really useful in practice. Now, the future. Well, the previous speaker mentioned the word machine learning. So that was the first time. I'll use it myself. In machine learning and AI, that is now incidentally taught in electrical engineering, in computer science, or dominated presence in computer science, people talk about feedback systems, and instead of encoders, they talk about variational autoencoders, and who knows, ideas of that sort will be useful along these lines too. So I apologize for taking too much time, but I already mentioned that it has been an honor and a privilege to have met Professor Rao in '82. Me, a rookie PhD student, him about to graduate. And I have clearly benefited from your impactful research, Bhaskar. Enjoyed every bit of our collegiality, friendship, and service to the signal processing for communications over the last 36 years. And I don't have a picture of our first meeting in '82, but I have a picture of our last meeting in the Signal and Image Processing Institute, where Bhaskar was awarded the alumni 50-year alumni award for the institute. And as they say, with a minor paraphrase, once a fellow Trojan forever. That's interesting to say, to come from a Greek, right? Yeah. Now, thanks for the invite. Heartfelt wishes for your recognition as an emeritus, full of joy. I didn't use the word retirement. Creativity, and above all, health. And thanks again, everyone. Questions are welcome.